So in this video, I'm going to show you how to set up the last problem on exam 3 that requires you to apply the parallel axis theorem in order to compute the moment of inertia of a composite shape. And the way that I'm actually going to do this, if you've looked at that problem so far, you notice that the way the book parameterizes the dimensions, they do it in terms of a variable a. And I'm going to show you an entire solution where the value of a is different. And we're going to walk step by step through why each number is the way it is. But the key thing I want to emphasize here is don't just enter the numbers that are on the next slide in your actual exam, because the value of a in the shape that I'm going to show you is a bit different. But you look at this, and what we're trying to do is define the moment of inertia of this shape about the y-axis. So in a composite-based approach, basically our logic is, hey, that's not a shape that I have the moment of inertia for in a table directly. However, if I were to chunk it up in such a way, like maybe I were to go to this peak and I were to draw a perpendicular line down, then everything to the right would be a triangle. And then in this area here, it's not quite a triangle, but if I were to draw a vertical line at A, or a horizontal line at A, then I would have a triangle on top and I would have a square on the bottom. And that's exactly what we're going to do here. We're going to decompose this shape into a triangle, a square, and a triangle. And the reason that we're going to do that is we know that we can look up in a table the moment of inertia of each of those shapes. And what we're going to have to do here, though, is in that table, that moment of inertia will be computed about a vertical axis that goes through the centroid. So we're going to need to apply the parallel axis theorem in order to translate that moment of inertia to the y-axis as shown. So easiest example of that, if you look at cutting out a square here at the bottom, its centroid is going to be right in the middle. So I am able to look up the moment of inertia of that square about a vertical axis through the centroid. I need to translate it over to the y-axis, and that's how I use the actual parallel axis theorem. I didn't paste this shape that they've drawn weirdly at that angle. It's just the way that the actual image was, and I didn't want to spend too much time trying to rotate it ever so slightly to make it look shaped. But if you notice, the first thing you have to do is actually to break this into a chunk. You need to take that composite shape and say this can be expressed in simple terms as a triangle, square, and triangle, exactly as we spoke of. Now, if you notice, their geometry, as I mentioned, is a little bit different. Their A is 3. Therefore, it's still kind of the same relative geometry. This triangle has a height of 3 and it has a base of 3. The square is 3 by 3, and the larger triangle has a base of 6 and a height of 6. So how are we actually going to go about applying the parallel axis theorem? Well, remember that for each shape, we're going to need to know the area. So for example, if we focus here on shape 1, this is a triangle, so its area is 1/2 its base, which is 3, times its height, which is 3. So that's where these numbers are coming from right here, 1/2 base times height. Now the question is, where is this number 2 coming from? Well, let's think about what that actually is in the parallel axis theorem formula. Remember that in the parallel axis theorem formula, if I can get it up here, you need to multiply the area by the square of the perpendicular distance from the axis about which you want to compute the moment of inertia to a parallel axis that goes through the centroid. So what that must mean is that for our particular problem, the centroid is 2 meters away from the y-axis. Well, why is that? Well, if you go to your table lookup for a triangle, remember that the centroid is 1/3 away from the peak side of the actual triangle. And here's what I mean by that. If we walk along the base of triangle 1, note that here is the peak. So if I go 1/3 of the base over, since the base is 3 wide, that means that the centroid, in terms of its x location, is 1 unit to the left. You could apply that same logic for the y location, but we don't actually need that information. But that's why they've drawn it where it is from, again, kind of viewing this end as your base in order to determine what the centroid is and y. Since it's 3 long, we'll go 1/3 of the way up, and that's how they're getting this. And in both cases, it's just going to be 1 meter set in to the left and up. But either way, what I'm interested in is if I were to draw a vertical line through the centroid, note that it is going to be 2 inches away from the y-axis. That's that perpendicular distance, so that's where that 2 is coming from. So area times a perpendicular distance squared. So the last question is, how are they actually determining what the centroid of this triangle is? And in that case, you're going to need to go back to the table that I provided and look at how you compute the actual moment of inertia of a triangle. And what they're saying here is if you're trying to compute it about one of the bases, so we're going to have to do we're going to kind of flip this when we actually apply the principle to the triangle that we're working with, because we're determining about an axis that's vertical versus horizontal, but it's going to be 1/36, whatever the side that the base width is from which you're actually measuring the moment of inertia, times the other base width to the cube power. So let's actually look at this. 136 base times h cubed. There is the 136. Now, in this particular case, since I'm trying to find, and just to show you, sorry, going back, I should have had a different printout of this, but remember that this moment of inertia is computed about the actual centroid here. So going through the centroid, it's just going to be 136, the base, which is parallel to the axis, and then the height, which is perpendicular to the axis. So in our case here, talking about the y-axis here, that is going to be the base, and that is going to be the height parameter. But since they're the same in both cases, it doesn't really matter. That's why you have a 3 and a 3 squared. And it turns out it's the same thing for the actual, this triangle as well, as we'll look at here in a minute. But going down to shape 2, how are we going to determine this? Well, you note that the centroid is going to be right in the middle. So in terms of the separation of a vertical axis that goes through the centroid and the y-axis, that's just going to be half of the base, or 1.5. That's why you have the 1.5 squared there. 3 times 3 is just the area of that shape. And how do I get the moment of inertia of a square? Well, you can just use the rectangular case when h and b are easy. I think that's why they're making these two parameters the same in both cases. But either way, it's just going to be 1/12, the base times the height cubed. And when the base and the height are the same, not here, then of course it doesn't matter which one you put in there. If we had more time, I would kind of go through some more challenging examples and kind of show you scenarios where you don't have that symmetry, but I'm confident if you got into this point in the course that it's something you can figure out. So finalizing for the actual triangle, again, its centroid will be 1/3 of the base away from the peak here. So if this is 6 inches wide, it'll be 2 inches to the right. So if I were to draw a vertical line through C3, I have a 2-inch separation just to get back to the edge of the triangle. Then I have another 3 inches. That's why that perpendicular distance is 5. Remember that you're squaring the perpendicular distance. That's your area, 1/2 base times height. And this is just your formula for the moment of inertia of that triangle again. So that's how it comes out to be, 533 inches to the 4th. Remember, those are the units for the moment of inertia. If you wanted to actually compute what the radius of gyration is, you could just add up these 3 areas, take the ratio, and take the square root. But that is all that you need for exam 3. So hopefully that was helpful for you. And good luck on that. And in terms of getting the final exam review up, I'm going to target to have it up probably by tomorrow night. Remember that it won't be due to Friday or even over the weekend if you need of finals week. So hopefully that'll give you plenty of time to get what you need to done. So good luck on exam 3, and reach out if you need anything, and I'll talk to you.